Okay, so welcome back, everyone. So today is April 4th, Wednesday. So this week we were going over the sampling distribution lecture, module number 8. And this was built upon the previous lecture, the basics of sampling lecture. And you will have mission number 6 that will be released. It will be due tomorrow. That will be due on that will be covering this lecture. So just wanted to have the opportunity to answer any questions, and we can go over the material together. If you don't have any questions. So this week we went over the sampling distribution lecture, which went over the central limit theorem, confidence intervals, and the basics of hypothesis testing. So we talked about the central limit theorem, which shows us that as we Sure. So Michael had a question. He said he's confused about if we take many samples of 10 people from a population, calculating a different sample mean for age, how would we calculate the average of these sample means? So let's go over that. And so here's an example as we were using the mean education, and we were sampling 10 people from the Iowa census data. And we took different iterations of that to find a mean education level. So here we took 6 years, and here we took, did another one, we found 8.8, and then we took another one, we found 6.5. So in order to find the average of those three, we would just sum them all up and divide by 3 to find what the average education is amongst those 3 samples of 10 people. So the idea is you can just sum all those averages up and then divide it by the amount of samples that you've taken. So no matter if it's 3 or 10 or 30, etc., you could just take the average of it. So typically we'd be doing that in a computer program like R, so we can keep track of it. And it's actually a fairly straightforward process just by using your R program. Otherwise, if you're doing it by hand, you would just you could just jot down for each sample that you do, each random sample, to calculate the mean, and then at the end you can just sum them all up and divide. But by using R, you can do it that much easier to find what the mean, the grand mean of all of those samples are. Does that make sense? And just as a reminder, the mean will be in the center. And then when we describe variability of that data set, we're talking about the standard error of the sample mean, which is calculated as follows. Take the sigma and we divide by the square root of n to get the standard error of the mean. So I'm just pulling up RStudio so we can take a look at how that looks practically speaking. So first of all, if you know the population mean and standard deviation of age, you would already know what you're looking for. So you wouldn't really necessarily take a sample distribution of it. The whole reason why we're taking a sample here is because we don't know what the true population mean and standard deviation is. That's why we use sampling to try to interpret and try to infer what the true population mean and standard deviation is. So, so for instance, you would take, as you suggested, you would take a sample and you would take a sample size of say 100, and then you would have different iterations of that sample. And then from there, you would find what the sample mean was amongst the grand mean of all of those different samples that you took. And then you could find the standard error of the mean as well. So the whole idea of this lecture is that when we don't know the true population mean and standard deviation, because we frequently don't, we can create a sample to infer what the population mean and standard deviation is.
I saw some. Right. And I also tried to come to solution.
So the standard error of the mean will show you the variability within your samples of how far the data spread is from the mean of your samples. So if you have big variety, a big variability within your data set, you'll have a large standard error of the mean. If you have a very tight data set amongst your samples, then you'll have a small standard error of the mean. So the idea behind the standard error of the mean is that if there's low variability, you'll have a low standard error. If you have a high variability, then you'll have a high standard error amongst your sample means, amongst the distribution of your sample means. So just from the formula, we know that as you increase your sample size, you're going to decrease the standard error. So as we see here, if we go from 10 samples to 30 samples to 100, 1,000, 100,000, the variability is decreasing amongst the data. And what I mean by variability is if we look here and we look at what the mean of this distribution is, you'd probably say it's around here, around 7, maybe a little bit less, 6.75, but you can see there's a variability. It's not a symmetrical data set, and you see that you have a big variability with your range being less than 4 to about 9. So you have a big spread of about 5 data points here. And as you're increasing, I'll just use this as an example, you can see here that the probability density is highest where your mean is of 7. So here, you can see here your mean of the sample means is 7, and here we have over 20,000 samples that have a mean of 7, whereas in these extreme points you have very, very little. So we can say that there is less variability in this data set because the most probability is clustered towards the middle, towards the center. So if you just look at it, you see it's very mound shaped, very symmetrical, and there's less variability amongst this data set than in the previous data set. So the standard error of the means is really describing this spread, this distribution of the means, the grand mean of all your samples. And as your sample size will increase, your standard error of the mean will decrease. So we can take a look here at R and go through some of these codes, because I know you were asking earlier of how this would work. So in this example, we could take a random sample of 10 people from the population and calculate the average years of education by using this code here. So this code says we're going to sample from the Iowa census data set. We're going to take a random sample of 10 people, and we're going to store that as a new variable called Iowa sample 1, and then we can take the mean of that by using this mean command, looking at the education variable within this new data set that we just created called Iowa sample 1. So I can run this code, and this will take a random sample of 10 people, and it will give us a mean of that particular sampling group in education years, which is 7.85. Now we can make a second sample by storing this new sample as a new variable called Iowa sample 2. We can run this code and find that the mean is 7.1 for that second one. And we can do it again. We can do it a third time we could just copy paste this code and then just change this to be Iowa sample 3. And we can run this. We get 6.2. And the way we can then so then what we could just simply do is we take the average of the three, which is 7.85, 7.1, and 6.2, and we could just average those. So you could do it either just doing it by hand, or you can use the mean command. So you could just do 7.85 plus 7.1 plus 6.2 divided by 3 to find what your total mean is. You get 7.05, which is right around where the true population mean is. And then in this example, we could take 500 random samples of size 10 and compute the average years of education for each of the sample, then create a histogram. And we can look at the shape of it. So here what we're doing is we're taking 500 samples of size 10, and we're storing that as a new variable called Iowa 500. And then we could take the mean and the standard deviation of this new variable called Iowa 500. So this will give us the mean in education of those 500 random samples of 10 people from this population, which we see here is 6.98, the standard deviation of 1.26, and we can make a histogram of it. So we're running the histogram command, and here we can see how that histogram looks, and we can see here that it's roughly symmetric, and we can see there's not that much variability here. That it's actually quite mound-shaped. You could say it's normally distributed. And then in this next example, we could do the same thing, but with instead of taking 10 people, we could take 100 people. So we can run this command. We could see it's even more symmetrical and less variable. We can see that the standard deviation, standard error of the means actually decrease substantially from 1.26 to 0.382. So it's just showing you, it's showing your proof that as you increase the amount of your sample size, you will decrease your standard error of the means here. And then if we increase it again, we can do the same thing. We can increase it to 1,000. We can take a look at that and how that's going to further change the shape and also change the standard deviation. So I'm just going to add a 0 here. And I'm going to run this command. So we can see here, the variability is further decreased. The standard deviation of the standard error of the mean has actually been reduced down to 0.12. So again, it's even smaller. So does that give you, does it make it a little bit easier to understand what we're doing here? So if you look here, if you even just look on the bottom, if you look at the scale, the range here is 6.6 to 7.4. And then the previous example, to look at that. So this is going back down again. Let's look at how the range changes that's automatically generated. 6.6 to 7.4, that's pretty tight. It's a range of about 0.8. So here you can see that as we decreasing the sample size, the range is now increasing. So you can see that the variability is increasing because the range is now from 5.5 to about 8.5, which is now a range of 3. Where in the previous example, when we increased our sample sizes, we saw the range decrease. The variability was decreasing to a range of only 0.8, so it was very, very clustered around 7. So when we're describing what the standard error of the mean is, we're really describing the variability amongst the sample means. And as we increase our sample size, that variability, that standard error of the mean, will decrease. And you'll see a tighter distribution centered around the true population mean. So that's the idea that we're trying to get behind. The whole idea is that in statistics, we don't know what the true population mean is. So in order to work around that, what we do is we take simple random samples. And ideally, if it allows both for resources and financially, and if we have enough participants, we'd like to increase our sample size, because then we have more confidence of representing the true population mean. So the greater our sample size, the more iterations that we have of higher sample sizes, the more confident we are that it's going to represent the true population mean. And that's what we're trying to explain here, what the purpose of this is. So hopefully that clears up that concept. Yeah, sure. So talking about the central limit theorem. So the central limit theorem, what the central limit theorem is saying is, so long as we have a large enough sample size, and for the purpose of this class, we're talking about samples of 30 or more, we can assume that the distribution of the sampling means will be approximately normal. So the whole point of this is that in statistics, we like dealing with normal data. A lot of our statistical tools and tests are based off of a normal distribution. And a normal distribution is that works around the z distribution. So we learned about z-scores and the z distribution, the normal distribution. So that's what we're talking about when we're talking about normally distributed data, Gaussian data, or symmetric and mound-shaped. These are all synonyms for the same distribution that we're referring to. So the central limit theorem says that if we have random samples of size n that's drawn repeatedly from any population with a mean of mu and a variance of sigma squared, then when n is relatively large, greater than 30 for most distributions, then the distribution of those sample means will be approximately normal. So that's a really great rule that we have in statistics that says that even if we don't know if a distribution is normal, if we take a large enough sample, large enough random samples of that population, then that distribution will be approximately normal, which is great for our purposes. So even if we have a skewed data set, a uniform data set, or an irregular data set, by drawing a random sample with a large enough random sample, we can now create a new distribution that we know will be normal. And this is just an illustration to show that. So here, what we're looking at is 3 random samples from these different distributions, these sample distributions. And here, we're looking at 20. And as you can see, that despite the populations which they come from being non-normal, as we increase the sample sizes here, it actually assumes a normal distribution. And if we're dealing with a fairly symmetric distribution, we can actually reduce that further to a sample size of at least 15. And if the distribution of the population which you're drawing from is already normally distributed to begin with, then your sampling distribution of the mean will always be normally distributed. So it's a powerful concept that allows us to assume normality for our sample groups if we have a large enough sample size. And the sampling distribution will be centered on mu, and we'll have the standard deviation of sigma over the square root of n, which is also the same as the standard error of the mean. So we only need these 2 values in order to model our sampling distribution based off of the normal distribution. So we can use the normal distribution to model our sampling distribution by centering it around mu and having the standard error of the mean sigma over the square root of n represent the standard deviation of our distribution here. And from there, we can just draw the rest out using our normal distribution. And so one way of doing this is, as we mentioned, we can convert our data into z-scores and have a normal distribution of z-scores centered around mean of 0 and having a standard deviation equal to 1. So this is the typical normal distribution, the z-distribution, with a center value, a mean of equal to 0, and the standard deviation here will be equal to 1. So that's what the central limit theorem is stating. It's stating that if we have a high enough sample size, we can draw samples from a population regardless of whether it's normal or not, and we can still assume normality based on the central limit theorem. And it will assume that sampling distribution of the sample means will center on mu and will have a standard deviation of sigma over square root of n. And to talk to your second question about p-values, we can talk about it in the context of the normal distribution. We can talk about hypothesis testing as well. So part 3 talks about hypothesis testing. And what hypothesis testing does is we set up 2 hypotheses. We have our null hypothesis, and we have our alternative hypothesis. And then we're able to run a given test and calculate a respective p-value for the hypothesis test. So the p-value is just short for probability value. and it represents the probability of obtaining data as or more extreme than the data we actually observed, assuming the null hypothesis is true. And the p-value can range from 0 to 1. And we say that a small p-value is significant, and we usually use a cutoff point, an alpha value of 0.05 for our significance level. And we say that a small p-value will indicate that the observed data and null hypothesis are inconsistent, and a large p-value indicates that they are consistent. So that means that if you have a significant p-value less than 0.05, you're going to reject your null hypothesis, and you'll conclude with your alternate hypothesis. If you have a large p-value greater than 0.05, you do not reject your null hypothesis. And let's go over why we do that. So let me show you that in the context of the normal distribution. Let me just pull up R, and I can talk a little bit more about that. So here I just pulled up our video. So just to explain what a p-value is when we're looking at a normal distribution, we are looking at the spread of the data in a normal distribution, and we want to look at the extreme value. So when we're running a hypothesis test, the idea is we have a null hypothesis that we're assuming to be true, that there is no effect, and we're checking to see if we can reject the null hypothesis by looking if our data is deviating from what the null hypothesis is. And so if our data is deviating so extremely much that it's not due to chance, then we will reject the null hypothesis. And the way we do that is by using this p-value. And what the p-value is looking at is it's basically looking at a z-score. So what we see here is for this normal distribution, we're looking at the 95th percentile here for a one-tailed z-test. So the critical value for a one-tailed z-distribution will be 1.645. That's the z-score for a 95th percentile. So that is to say, if we're looking at a given hypothesis test, we would have to have a result that falls in this light blue region in order to reject the null hypothesis. Because this point here is the 95th percentile, represented by the z-score of 1.645. And if we have any result that's more extreme than that, we would reject our normal or null hypothesis and conclude with our alternate. If we don't see that, if we see that the results of our hypothesis test falls in anywhere in the red region, we do not reject the null hypothesis. So when we're talking about the p-value is representative of a probability, and it's the probability that we have a result that's at least as extreme as that value. So the probability of getting a random number that's as extreme as that value. And if you have a two-tailed test, you're going to look at both sides of the normal distribution. So in the previous example, that was just looking at a one-tailed test. In this case, you could actually look at a two-tailed test. So this is representative of a 95%. So this is looking at a two-tailed test with each of the two tails having 2.5% on each of those two tails. And in the shaded green region, that's actually 95%. So this is what representation of a hypothesis test using a 0.05 alpha would be for a two-tailed test. So in this case, you're looking for whether your data is falling within the blue or the red region. If it's falling within this green region, you do not reject your null hypothesis. If it falls in either the blue or the red, you do reject your null hypothesis because that's a significant result. And we'll learn more about p-values and the significance of the different p-values as we go on with the rest of the following lectures. But just as an introduction, this is the p-value is representative of a probability value. And it shows you whether you should be rejecting or not rejecting your null hypothesis in the context of a hypothesis test. If you have a small p-value, less than 0.05, that's a significant p-value. You'll reject your null hypothesis. Otherwise, you do not reject your null hypothesis. And the critical values for a two-tailed normal distribution will be 1.96. So 1.96, positive 1.96, and negative 1.96. Those are the two critical values that represent a two-tailed normal distribution. So just to summarize that the null hypothesis is denoted by H naught, and the alternate hypothesis is denoted by this HA. And the hypotheses can be either one or two-sided. So in order to perform the respective tests, you're first going to have to state your hypotheses in terms of a one-tailed or a two-tailed test. And you will assume the null hypothesis is true, and then look for data to either reject the null hypothesis or fail to reject the null hypothesis. So that's how you perform your hypothesis test. And there's two types of errors in the context of a hypothesis test: an alpha error, which is known as a type 1 error, and a beta error, which is a type 2 error. And these are also representative. They're also known as a false positive or a false negative. So a type 1 error, an alpha error, is a false positive, and a beta error is a false negative. So a type 1 error is rejecting the null hypothesis when it's actually in fact true. And a type 2 error is failing to reject the null hypothesis when it is false. So we have two types of errors. And then as far as the p-value is concerned, it's short for a probability value, and it's the probability of obtaining data as are more extreme than the data we actually observe, assuming the null hypothesis is true. So that's how we understand what the p-values represent. So we can go through an example. So we can use an example of aerobic conditioning by looking at whether students in the class have a similar aerobic conditioning as the general population. So in the population, it's known that the mean heart rate is 69 beats per minute with a standard deviation of 6 beats per minute. And we're using a set of students as a random sample in order to investigate that. So first, the steps of starting a hypothesis test is we're going to set up our hypotheses. In this case, it's a two-sided hypothesis test with the null hypothesis mean equal to 69 beats per minute, and the alternate hypothesis being that the mean is not equal to 69 beats per minute. So we calculate what the 95% confidence interval is based on our sample data by taking our sample mean and adding and subtracting the z statistic 1.96 times the standard error, the sigma divided by the square root of n, which is 6 over the square root of 20. So in this case, we have a sample size of 20. We find that the standard deviation is equal to 6. So we can come up and we know that we find that the mean beats per minute amongst our sample is 60. So we can come up with a 95% confidence interval from this data, and we find it's equal to 57.5 to 62.75. And from this confidence interval, we can look for whether the null mean of 69 is contained by that confidence interval or not. In this case, because the null mean of 69 is not included in this confidence interval, we reject the null hypothesis because it's outside this confidence interval, meaning that our sample is inconsistent with the population. So we're going to reject the null hypothesis, concluding that they're actually different. So if the null hypothesis mean was included in this confidence interval, we would not reject the null hypothesis. But in this case, because it's not included within this range, it actually falls outside the range, we conclude that we'll reject the null hypothesis and conclude that the sample mean in this group is different from the population mean of 69 beats per minute. So in this case, if we were to calculate a p-value for this given example, we would expect that the p-value would be less than 0.05 because it was a significant result here. And we can actually look at it because if we actually looked at a 90% confidence interval, you can calculate that and see if it would encompass this or not. So a 90% confidence interval would change your z-statistic. It would go from 1.96. It would actually go to go from 1.96 to 1.65. So we can actually look at how a 90% confidence interval would compare. And we could also look at a 99%. So let's look at that. So this will represent a 90% confidence interval by using 1.645 instead of 1.96, which was used in the previous example for a 95% confidence interval. So in this case, we could take our mean of 60.11 and we can add 1.645 times 6 over the square root of 20. We could find that the
Yes.
So we can find what the confidence interval would be in this case. So it would be 58 to 62. We could also look at a 99% confidence interval. So this would be the z-statistic that you would use for a 99% confidence interval. So you would then use this score of 2.576 times 1.3416 to get 3.45. Then you will add it to our 60.11. To get 63. So as we can see here, even with our 99% confidence interval, we still don't see 69 appearing there. So we can be very significant that that will reject our null hypothesis. In this case, because with a 99% confidence interval, it doesn't include that mean of 69, we could say that we are 99% confident of that. So we can say that the alpha value is less than 0.01. Because even with the 99% confidence interval, it still does not include the null mean of 69. So we can say that the alpha value is less than 1% here. So you have less than a 1% chance of making a type 1 error. And that's how we can understand what a p-value is. The p-value is representative of your probability of making a type 1 error. Remember, we said type 1 error is a false positive, rejecting the null hypothesis when it is in fact true. So hopefully that helps clarify some of this material. If you have any last questions, there's about 5 minutes left, so I'm happy to answer them. Otherwise, feel free, you can send us an email to follow up. And I'll also be having another session tomorrow at this same time. Yeah, so the p-value will represent the probability of a type 1 error. Because your alpha value, well, so your alpha value is, the alpha value is representative of a type 1 error. So your p-value, for it to be a significant result, should be less than your alpha value. So your p-value is, what the p-value is the probability of getting getting a random result that's as extreme as your value. And the alpha is representative of the probability of getting a type 1 error. So not to say the p-value, but the alpha value rather is your probability of getting a false positive. So in other words, if you have a 95% confidence interval, that is to say you have a 5% alpha, which is a 5% chance of having a false positive. So I hope that helped answer some of the questions you had tonight. Best of luck with the mission, and let us know if you have any additional questions. Great. So best of luck, and see you guys tomorrow.